And now for something completely different. So consider the problem of the longest common subsequence. We're given two sequences. Here we're doing the sequences of letters, but those can be just sequences of numbers. And you want to find the longest subsequence that appear in both sequences, right? So, for example, here we have this string. So we can, for example, take the B and take the A. And now we are kind of not in very good place. We can take the D and the D, right? So this is length 3, right? We found but this is a bad sequence because it has length 3 that is common. But we can do better if you think about it for a second. You can take the A with the A, B with the B. My ability to do this badly is really impressive. So let's try again. A with the A. B with the B. Yeah, that's good. A with the A. And D with the D, right? So we found a subsequence abad. Okay, so this is a subsequence of length 4, right? So given those two sequences, I would like to find the longest common subsequence. It's a very natural problem, right? It's kind of give me the common structure of the two things. So we want to get to a dynamic problem for that, and it's easy to observe that this is really very similar to edit distance. So again, we have those two strings or two sequences given in arrays, and we define the longest common sequence of the prefix of the first I element against the prefix of the first J element in the second sequence, and we have to take care of the boundary cases. If I equals 0, J equals 0, an empty sequence against a sequence, the longest common subsequence is of length 0. Otherwise, we can look on the last two elements in the two sequences. If they are not equal, we cannot really align them from each other. So we cannot include them in the common subsequence. So we call recursively either on the prefix of the first string, where we look on the first I minus character, or the second sequence on the first J minus 1 character, and we take the maximum, unlike edit distance, which we take the minimum. Otherwise, if the last two characters are equal, we might include them in the subsequence, the longest common sequence. So we have another possibility, which is we include it in the subsequence. So we get 1 for that, and then we call recursively on the longest common subsequence of I minus 1, J minus 1. Right? And that's the recursive function. It's very similar to edit distance. You throw it into the same old dynamic program, approach, and you will immediately get an algorithm that has running time mn and O of m space if you do the space reduction tricks. So that's it. But in fact, if you think about it a bit longer, you would realize that in fact longest common subsequence is just edit distance under cover. You can reduce longest common subsequence to edit distance, and the reduction is kind of simple. We have to play with the cost function. So the cost function, what we do is that if we're trying to match two characters or two values that are not equal, we set the cost to infinity. So the edit distance can no longer afford aligning two characters that are different. And now for matching a character with itself, instead of cost 0, like in the old game, we set it to 1. Why I set it to 1 will become clear hopefully shortly. And also we set the price of 1 as the cost of insertion and deletions. Okay, so what happens? The worst thing you can do, of course, is just if you think about it at a distance, is just to put first have the first sequence and then I have the second sequence if you think about it as alignment, right? So this would have cost mn. So the maximum edit distance under this pricing model is m plus n. Now, what we really want to do, we want to find the longest common subsequence, namely we want to find an alignment that maximizes the number of columns where they are equal, they are the same, right? So every time you find a column that they agree with each other, you eliminate one column, right? You eliminate one column where you have to pay 1, right? All column, the situation is that now every column of the alignment you have to pay 1. Either you pay 1 because they're the same character aligned, or you have to pay 1 because it's insertion and deletion. So finding the maximum longest common subsequence is equivalent to minimizing the number of columns in the alignment, and which is exactly what this edit distance function does. So you compute the edit distance under this pricing, and if you take mn minus the edit distance, what you get is the longest common subsequence. Okay, so one needs to look at it for a bit and verify that it makes sense, right? So as we said, if we do the stupid thing, the edit distance is going to be mn, so this is going to be 0. Then we don't have any common subsequence. Otherwise, for every column that they align, right? Previously we had 2 columns. Let's say that this was x and this was y, right? So we paid 1 and 1 for both of them, and we x and x, right? They have to be equal. We had a column like that, and we replaced it by column xx. The column xx now have price 1, right? So we reduced the price from 2 to 1, right? As such, the edit, sorry, this is not edit, this is of course the LCS price. The LCS price as such is going to be exactly this. So computing the edit distance in this under this cost function is equivalent to the longest common subsequence. Okay, so it's a cute reduction, and you might have to look at it a bit longer to make sure that you really believe me. Okay, this is it.